Okay, guys, so let's discuss again some of the formulas that we're going to see pertaining to capacitance. All right, now you'll cover this more extensively in the lab portion, but what we're going to do is just look over some of the concepts relating to capacitors. So I have here um, a power source, okay, with a very simple circuit. And this power source is actually, it's hooked up strangely to these two plates that are parallel to each other, okay? So what I want to do is if I hook up, so I'm going to use this symbol a lot for power source, okay? But if I hook this up to some power source here, okay, and I allow current will want to flow, right? So if we say one side is positive and one side is negative, um, my electrons are going to want to flow through. If they could, if this was a fully connected circuit, they would want to flow from the negative side to the positive side, and they would want to equalize this and make it zero, right? But right here, there's a gap. They cannot do this right now, right? So what's going to happen if I hook this up and I have some gap, but I've got plates here, is that my charges are going to move around, right? And then they'll start to build up. So here's one, here's one, here's one, and they'll start to build up here on the edge, okay? But also, these positive charges don't want to be near each other either, so they'll start pushing away from each other if they can, right? And we're going to do these in a different color, but these will start building up on this side because not only do they not want to be close to each other, but they want to be close to these negative charges. So they'll start building up on this other plate. So what I've essentially done here is I've created another source of energy right here. I've kind of stored the energy that was in my battery over here now. Because what's going to happen if I were to remove this battery now? Let's say I remove this battery. Well, all my charges were still here. They can't go back into the battery. I've disconnected. And all of my positive charge over here is still here. It can't go back, right? So they're kind of stuck here now where they have to stay here. So I have now essentially stored energy. This is what a capacitor does. This is the main function of a capacitor, is to store some energy, or, okay, alternatively, the way that we can use this is I have a circuit with a capacitor in it, and I don't want any charge to flow until a certain point. There is something called a breakdown voltage of my capacitor, where if I put more voltage, these will start to hop over. They'll start to actually go. They really want to be together so badly once I put a certain voltage on this that they'll start hopping over, but not until that point, right? So I can actually use this as a switch where I say, if I put a small voltage on here, I want you to get stuck right here, charges, don't move, don't flow. If I put a large voltage, okay, now I want you to start jumping over and I want you to flow through my circuit. So it allows us to do different things in our circuits. But basically, the way we're going to talk about capacitance, and our unit here is farad, which we use F as my abbreviator, okay? And it's basically a measure of how much charge can I store, okay, when I apply a certain voltage. This voltage, remember, is like a pressure. This is my electric pressure. So how much charge will build up here for every unit of electric pressure, my voltage, okay? So here, let's go ahead and mark this. This is my charge. This is my voltage, okay, and I'll put a little note here. This is electric pressure, okay, and this is my capacitance, of course, right? So what are some of the things that actually affect how much charge we can build up on here, or how easy it is for us to build up charge on here? Okay, well, let's kind of take a look at this. So it seems that if I were to make these plates further apart, okay, so we're going to start with the distance between these plates, okay, this right here, this is my distance between my plates, and what happens is if I were to make these further and further apart, then yes, my positive charges on this side, they don't want to be close to each other, but if they're further and further away from these negative charges, right, let's say I kind of do this out here, and I put a really big gap, well, these charges aren't really feeling the attraction from these negative charges because they're so far apart. Remember, my force between these, it depends on r squared inversely, right? So if they're super far apart, they really don't care about each other. So the further apart my plates are, the less charge wants to build up on the edges. So this is my distance between my plates. So as here, you can see I have a little formula down here. As my distance gets larger, my total capacitance will go down, right? If this denominator gets larger, this will get smaller. Okay. Next, what if I use bigger plates? So now, I'm going to replace these. Or you know what? I just ran out of room when I did this. Let's go and slide these down. So, what if I make these plates much bigger? Well, when I hook these up to my battery, remember that one of the limiting things is these positive charges don't actually want to be together, right? I can force them to be together based on they want to be attracted to these other charges, but also based on the voltage that I'm using to push them. But they really don't want to be together. But what if I had these 4 charges, but I gave them here, let's do this. I made this bigger, so that now these 4 charges don't have to be so close together. Now they could be much further apart. And then same thing with these guys right here. These guys could be much further apart. Now these charges are a lot happier than they were before. It's so much easier to get them to be in this configuration versus when they were tightly packed together, right? So making my plates bigger makes it easier to store more charge because they're not so packed closely together, okay? So increasing the area, if we make this a 2D plate right here, 2D plate, increasing the surface area of my plate is going to give me more opportunity to store charge. This will increase the charge I can store, so it'll increase my capacitance. So area here, this large A, is the area of whatever my plate is on either side. Okay, this is assuming, just so you guys know, that both of my plates are the same size. Okay, lastly, I have these 2 little constants here. One of these we've already seen before. This is my permittivity. This is 8.85 times 10 to the negative 12. This is fine. We've used this before. Remember, this is 8.85 times 10 to the negative 12. This is fine. But now we have this new constant right here. And this, okay, is my dielectric constant. Okay? Basically, what this is it's a buffer in between these 2 plates. It's describing something about the resistivity, right? Not resistivity exactly, but the potential for this plate here to be polarized. So what I have when I have my dielectric, I can put something in between here, and it'll affect how much charge I can build up on either side without it breaking down, right? So my dielectric here is something that we'll usually have to solve for, but we don't have another formula for this right now. So what we're going to do is we're just going to treat this as the This right here will be whatever my material between plates. Okay, whatever my plates have in between them is going to dictate this value right here. Just so you know, most of the time we're using K equals 1 for vacuum. This is nothing. Okay, there's nothing between my plates. I'm only looking at the size of them and what voltage is on them. So my K equals 1 here, if there's nothing in between my plates. Okay, so this will kind of wrap up us looking at two of the main formulas we're going to be using for capacitance in this module.